Good afternoon, all. Those who don't know me, I'm Bassam Lali. I'm Professor of Mechanical Engineering here at CAST and a member of CCRC. Gives me great pleasure to host the session or to be the moderator this afternoon. We have three speakers before the coffee break and then two speakers before the end of the day. And from there, we're going to have dinner in the afternoon, in the evening. So our first speaker is Ruud Eggels. Many of you may know him. He, of course, is a combustion specialist, mostly CFD work that he does and known for at Rolls-Royce. He has an illustrious career. He has spent a lot of time producing really groundbreaking research, and he's sort of also involved in the Combustion Institute and have a board member role in the International Combustion Institute. So without further ado, I'm going to ask Ruud to give us a talk for around 30 minutes, and we're going to have some questions and answers, please.
Okay, thank you. Yeah, first of all, also thank you for the invitation to give a presentation here. It's very interesting to be here. You've seen a lot of presentations on conferences from CAUS. I've never been there. So it's, yeah, it's very good. What I want to show is that what we've done within our company for the last couple of years on converting gas turbines, Aero-Engines to hydrogen. And of course, it's not my work which I do by myself, but it's a lot of people, and only a few people are here. And it's a combined work which has been done in Rolls-Royce in Germany, where I work. We're located close to Berlin. But also a lot of work has been done in Rolls-Royce PLC in the UK. Yeah, first of all, one slide of introduction is like what our company, our strategy is to reduce like the CO2 imprint. It consists of three pillars. One of that is just looking at alternative fuels, like something different as liquid fuel. That can be high electrification or hydrogen. That's what we'll talk about. Will be today. The second one is about accelerating the availability and affordability of SAF, so that's sustainable aviation fuels, which are very similar to kerosene, but then in the end have no CO2 imprint or little. And the third one, this is something actually, it's more or less one of the important ones, is also to continuing the efficiency of the current engines. It's like somebody said, like the best thing is to reduce the impact on the environment, is not to burn the fuel. So that's also one key thing which we continue to do. The second slide, giving it a little bit of introduction of where we can do what. It's like there are different alternative things to get away from kerosene. You can do electric, but actually in the end, it's also something you only can do for very relatively small airplanes. If you go to like the regional airplanes, it's not possible anymore. And if you look at regional, that's actually, and the narrow body, small, medium engines, that's where we work in Germany. Then we're looking at using SAFs, sustainable aviation fuels, and also then looking at hydrogen. You also see hydrogen fuel cells. That's something which we're following and doing some work and research on for a long time, but also this is being thought because of the weight and size for something for relatively small airplanes. And if you look at the very large airplanes, the wide bodies, that's where maybe you can do something more electric, but also the key thing is actually where we're looking at is SAFs. So on hydrogen, we had like, there's of course a big push from government. So we have like 4 big projects where we're working on hydrogen, and they're funded by national funding and European one. And the first one where we started with in Germany, it's called Wotan, it's a German name. And then we also have a UK program which is called HIGHEST, where we also develop on the hydrogen technology. Then we have two European projects. One is called Hestia, where we work in cooperation with many partners within Europe on developing technology for, and also fundamental stuff for hydrogen. And then we have another one, a European one, that's actually the biggest, that's Cavendish. And then I will quickly go through all the project, what we do where, and then we'll come to more details about what we have done. Yeah, the Wotan, the German project, it's a few things which we do there. We look at fundamental things. It's like with university, further develop CVD methods for hydrogen specifically. But also like developing hydrogen injectors, and you see two examples here in the pictures which you developed, manufactured, and finally then also tested. Where we do, and the testing consists of two things. It has been mentioned before, but we distinguish between low and high TLL. TLL stands for technology reality level. And yeah, it's divided in certain classes, and if we reach TL6, then we can try it in an engine, first on ground and then fly. So low TLL is where you look at a single injector in a test rig and then see how things performs. And this, of course, in cooperation with partners, with the DLR, the German Research Center, and also with the Technical University in Darmstadt. The HIGHEST program, they're doing things similar, but they're looking at a little bit more novel and injector concepts like the micromixer concept, where you see an idea on the bottom, how it could look like. Also here, we do some numerical development to be sure that what we're doing in CVD makes sense. Also here, we are looking at the preheater, and the preheater with preheater, I mean, is that if you have a tank with liquid hydrogen, then we don't burn it liquid, don't bring it liquid to the engine. It will be preheated first and gaseous supplied to the combustion chamber. So that's where we need a preheater for. And also we do experimental work. And also here cooperation with Loughborough, which will do a lot of experimental work, Cranfield, Cambridge as well, and Swansea. There's a European project, which is a much bigger community. You see on the left-hand side all the partners. And here that's something you can do very well with in such a project, is look at the fundamentals of combustion. And also over here in this project, we look at, many people know this this Hylon burner. That's good because you have experimental data. You can compare your CFD results against it, and get an idea of how good you are. But also we do some development on ejectors, AQL ones. I come back to it, what it means. And also to multi-point micromix injectors. And we also will manufacture them and test them as well. And actually this project is being coordinated by Safran. There's many other partners included. Then the last project it's called Cavendish. Actually, was actually originally a French guy which moved to UK and invented hydrogen. So that's the reason why it's called like that. And here we will look at performing a test, an engine test. That's the ultimate goal, to do an engine test on hydrogen. And here we decided for a retrofitful concept, because that's something which has the lowest risks, and it's to achieve that, because it's only a 4-year program. And we also decided that a Pearl engine on the left-hand side will be the donor engine. This will be then the engine which will convert the combustor to hydrogen. And of course, it's all linked to the other programs where we look in more detail to the injector development, and here we go to higher TLL levels, and we go to TLL 6. In the end, we will do an engine test in this program. Yeah, and actually it's much more than that. So it's we will go up to an engine test within Rolls-Royce, but we also have other partners which look at tanks and fuel systems. And also about things, how you integrate the aircraft into an engine. So there are also engine manufacturers in here, aircraft manufacturers in here. We also develop like concepts, how you could, in the end, can, the route to fly, how you can, in the end, can introduce it into service, and how you negotiate with the governments and all the regulations. Okay. So, okay. So now going a little bit deeper into how we developed the technology and what we did is that this is one of the initial phases. We looked at different concepts. And if you look, you'll see like slices from an existing combustion chamber from a Pearl engine. And on the top, you see like an injector which is retrofittable, so you don't change the combustor, only exchange the injector. And if you go down, then the possible reduction in NOx will reduce, but also the complexity of the system will increase. So the simple thing that you can do is where we start with is just exchange injector and leave everything else the same. And it's called ARCO-L because it's a rich quench lean system. So in the primary zone, it's lean. See whether you can get with the mouse. Oh, okay, I'm pressing the wrong button. Oh no, I lost control. Well, okay. Can you see this? No, can't see it. Okay, where it's red, it means like a high temperature. That's the primary zone, it's very rich, and then additional air is injected to it, and then you quench as quickly as possible. And in the end, a gas turbine also always operates on lean conditions, otherwise it would get too hot. The one below, it's like a flux concept. Flux originates from flameless oxidation. In the end, well, hydrogen probably you get flameless oxidation. You don't see the flame. But that's where you premix. No, we don't premix here, but at least you introduce the air and hydrogen at very high velocities, so then they mix with burnt gases as quickly as possible, where we can go like 20–30% lower of NOx. If you go one step further, you go to micro mixers, where you inject hydrogen via a lot of holes and air around it, and it gets complicated to manufacture it. But then we did some assessment, you get like 60% lower emissions. And the bottom one is just a pure numerical one, where you premix everything and say, okay, everything is perfectly premixed, and then that's the ultimate lowest emissions you get. That's about a factor of 10 lower is what we currently have. But we have what I show here, and that's where we started with to bring it up to maturity, is that we chosen to have like start with the ARCO-L concept, like the top one, just change the injector and don't change the combustor, because that's the lowest risk. And we, from the studies we did initially, we expected that we could get similar NOx emissions. So the injector development, so is what we did. We started this from day one. We started to use CFD as much as possible, and looked at different concepts. We looked at literature, what people did before, and yeah, at least try to do things which are similar. On the left-hand side, again, like a picture of how the combustor looks like, and so to be able to do CFD, you first have to create a CAD model and to make a geometry, run CFD. And then one thing we did to compare, like, for instance, NOx emissions with kerosene, is that we chosen the AFRs, the air fuel ratio for hydrogen, such that we get the same exit temperature of the combustor. And in real life, then an engine will operate slightly differently. But actually, this is a pessimistic view because of the thermal properties of hydrogen and the CPs, in the end, you can run slightly leaner with hydrogen. So, but assuming they get the same temperature, that's a fair and good assumption. And then we did a lot of CFD, and then we do it with our own in-house code. And initially, we didn't do a lot of changes, actually almost nothing. And most of the stuff of the CFD calculations we did is based on RAMs because it's quick. You can do 4 or 5 geometries in a day. And then with FGM, flame-generated manifolds, that's been used as the combustion model. And we only had minor changes to be done to use it for hydrogen. We don't have preferential diffusion included, and that's something which we've investigated in one of the research projects to see how we can incorporate it and to see what impact it has on the results. Yeah, and then we computed like NOx emissions and compared it with, we compute emissions at the AKL operating conditions. These are conditions we specified for the regulations. So that's important finally to compare the NOx results compared to what we get on kerosene. Here's some examples of the temperature on the left-hand side and the NOx emissions on the right-hand side for combustion systems on the top running on kerosene and the hydrogen on the bottom, like using hydrogen injector. And what you see strikingly is that, and that's what we expected, but is that you see in hydrogen you have higher peak temperatures. And also, if you look at the primary zone, the NOx emissions are also higher for hydrogen. But what we have seen that finally, if you look at the X of the combustor, the NOx emissions are very similar. So actually, when we started this project, then we had 2 concerns. The 2 main concerns is one of them was whether NOx could be comparable or should be. We also had. There were some people who estimated that NOx would be twice as high. And the second big thing where we were afraid of was thermoacoustic instabilities. And I'll come back to it later. But it's very difficult to predict this with CFD, especially if you're looking at a lot of different configurations. So this one example, and I'll show a little bit more, is that our CFD prediction showed that it should be comparable emissions with regard to NOx. Very interestingly, and actually only did it recently, is that how to look at the NOx emissions in your combustor is to put a plane through the combustor at different axial positions and then integrated NOx finally in grams per second. And if you compare then the hydrogen with the kerosene, then you get very similar results. Actually, here, at the end, the hydrogen is slightly lower than the kerosene. And that's something which, even after all this year, is that if you look at these pictures, then your eye is attracted to this hot blob. And then you integrate by eye, and it always goes wrong. So if you numerically integrate, that's much safer. The reason why actually it is that because you have high peak value of NOx, but that's in the recirculation zone. So finally, it doesn't contribute to a lot of mass in it, which goes to the exit. The other thing is that, jumping a little bit ahead later on, is that we always overpredict the NOx emissions when we model a combustor on kerosene. We also do on hydrogen, but actually the overprediction on hydrogen is not as much on kerosene. That's something we don't understand yet. And that's the reason why, in the end, the emissions are very similar, but numerically, we end up with slightly less NOx emissions for this at this condition. Yeah, what I said before, most of our CFD predictions were based on RANs, and of course, you asked the question, especially in this community, is GRANT good enough? Of course, if you look at local effects, it's not. So therefore, we also looked at LES for a few limited operating conditions and a few limited injectors. And if you, on here, an example on the left-hand side, you see the velocities, and of course, the local changes can be high, but overall, like the shape and what's happening, it's very similar. If you look at the instantaneous picture on the right-hand side, of course, that's very different. So that was the velocity. If you look at the temperature, it's a similar picture. It's like, yes, it's locally different, and of course the mixing is different. It's much better predicted in LES. But like the global picture of what's happening in the zone and then comes out at the exit, which interests us most, it's comparable. It's not really different trends what we're seeing. And here the final picture on NOx, here the difference are even bigger. But also if you look at any end and the exit what's happening, then it's not that much. Yeah, and the other thing to look at is I looked at, because we're using the FGM model where we also can evaluate the reaction progress. And if you look at what's happening in the combustor, is that everybody knows hydrogen burns quickly, but it burns very quickly. And of course, we have higher temperatures in our combustor, so and high pressure. So the reaction zone is very, very, very small. And that's but I also, something to look in detail, but that's also why I believe that preferential fusion locally has a big effect, but only in the frame front, which is very small. So that's probably why brands are still doing a reasonable job for this. Yeah, just this more or less what I said is like, yeah, you have preferential diffusion, of course, which is important and can make a big local change, but the reaction zone is very, very small. And also, yeah, turbulent diffusion is much, much bigger than the laminar diffusion, the preferential diffusion. But nevertheless, is that I showed, and we have a lot of research projects where we, in cooperation with universities, are looking to improve our model capabilities, and that's going on. But this is going in parallel with the technology development, and the technology development you use, yeah, what you have at that moment. You don't want to wait 4 years before you have a more advanced model to be used. So getting a little bit deeper into the injector development, we looked at different concepts. And what do I mean different concepts? I showed 2 of them here. I can show them because they're published anyway in patents. On the bigger picture, an injector which has similarities with our kerosene injectors, but it's different in the fact that it has, you can see the top picture here of how it looks like, have a relatively small outer region where the air comes through, and it's not swirled. And the inner passage, also air comes through it, and in between the air passages, hydrogen injected. And the idea is that you have relatively high velocities, so therefore no swirler, to keep the flame away from the injector. So that was the concern we had. If you start to, we don't premix, but at the time the air and the hydrogen meet, they will mix, and then you can start to burn. So therefore, no swirl to have high velocities, and also there are some theories about thermoacoustics that this is coupled to the voltages which are generated and precessing voltage scores. So therefore, we also want to assess whether it really is like that in reality. The other concept, which you see the details on the right-hand side, it has a bluff body, but the thing is that in the center, the hydrogen is injected central here, and then air is around it. So in the end, you will create a very rich primary, even richer primary zone. And the thing is that the advantage of that is that you keep the hydrogen away from the walls. So here, 2 other concepts on the bottom. The top ones I presented before, the bottom ones. They're very similar to our kerosene injectors. The only thing is that the passages where the fuel comes through are much bigger because of the low density of hydrogen. And one, the fuel is injected with the holes, you see, and once it's injected by a slot. And right outside the temperatures for all these different combustors. And you can see where the hydrogen comes in, which is gold, which is the blue one. Yes. And CFD land, they all looked okay. We did, of course, iterations to be sure that the temperature to the wall is not too high and that the temperature to the fuel injector is not too high. And then what we did, we tested a range of fuel injectors at low TRL, okay, 5 minutes conditions. That means like single sector reactors, and then in the end, these 4 have been tested in the full annular combustor, which is like the real combustor, which is also in the engine at full conditions. Yeah, I only have 5 minutes, so I have to go a little bit quicker through it. You see on the top row different test rigs we did. We started with to run at atmospheric conditions to see whether the things work at all. And then we went to higher pressure rigs, the IP rig in Loughborough. We had a 3-sector rig, a DLR running up to 10 bar. And then on the right-hand side, you see like the entire combustor, which we tested in DLR in Cologne in 2023. So I jumped a little bit through this because otherwise I don't get to the results. So this is results of the 2 injectors which I showed before at a sector which has 3 injectors in there, and in principle, we went to realistic operating conditions to be sure before we went to this full combustor test. And actually, all of these combustor of the injector concepts worked without any didn't know there was sound in there. Worked well. And then we went to the very big test where you see on the right-hand side the test rig. Here in the middle, you see the entire combustion system. You see these very big pipes for hydrogen, and this is the entire ring of combustor. And a close-up of a fuel injector and how it looks like. So I'm just going back. So okay, going back. So what we do, we measured like the NOx emissions. That's one of the things which is very important for us to get combustor exit temperatures. And also we did a separate test for thermoacoustics. In the end, we did 2 test campaigns for 2-3 days, and we burned 5 tons of hydrogen. Which at that time was about half of the produced green hydrogen in Germany in a week. And maximum, and 5 tons is what DLR actually could store at that time, maximum. So you see a result of the combustor exit temperature. We don't measure the temperature directly, we measure the water content. And from that, we calculate the temperature back from equilibrium. And you see the bottom one is the test, and the top one is the test, the bottom one is CFD. You see the pattern looks very much similar. And this is the NOx emissions. I will jump to the next one. I like it a little bit more. You see the different colors mean different injectors. And you see 4 groups of dots. These are for the ICAO operating conditions for which we have to certify. And on the right, on the horizontal axis is like the measured NOx emissions, and the vertical is what we predicted before. And you see a very good match. And also the ranking between the different injectors was predicted well. And that's something I'm very proud of, that it worked very well. Because initially a lot of discussions are, do we really meet like similar emissions for kerosene and for hydrogen? And that was not clear. Another thing you also can see is what I said, like if you look here at the measured emissions at 100, you end up at 140 for CFD. So we always overpredict in CFD NOx emissions, and for kerosene it's even more. So this is one of the almost the last slide. So just comparing the total NOx emissions, and it has to be, it's compared to the regulations which are defined in CAPE, and our current kerosene on this engine, the gray one, is we have like a margin of we reach a margin of 28%, how we say that, below the limits. And if we move to hydrogen, then we have slightly more emissions, about 10 to 15%. But yeah, you have to keep in mind this was our first kind of step into the hydrogen. And actually what it means, it even would be certifiable. It's high, but it still is already certifiable, and that was the first step. That's something which you didn't expect. The next one is like, we were very afraid about thermoacoustics, and we didn't have any problems with thermoacoustics as well, which we didn't expect. You see on the left-hand side some plots where we normally make. It's like the pressure, the maximum pressure we see, thermoacoustic pressure as function of the inlet temperature, combustor inlet temperature, and the function of EFR. In reality, the engine runs at only in one line, but then we measure this map to see where they have certain positions. We have thermoacoustic instabilities. The plots for 3 variants, and everything, only the red points which should be in concern, and we don't have any red points at all. An engine wouldn't even hit these points which you see here at all. And one thing which is very interesting for me is that, because what I said before in the beginning somewhere is like I developed one injector which didn't have any swirl in the outer. You see, and the idea was behind having little thermoacoustic instabilities, and actually that's the variant number 1. So actually, we still don't know where it works, but it's at least the one which was the quietest. So, and then the final slide is like, yeah, summary. We started a journey to develop like technology for hydrogen a couple of years ago. And yeah, what we did, we looked at different concepts. We tested them on different low and high TRX. And we are very happy with our results, because we expected a lot of problems. And we looked at different concepts because we said, okay, definitely 1 of 2 or 3 will fail. But actually, all of them worked, yeah. So one of the next steps will be that we do another full ANA test by the end of this month. And then next year, we will run an engine on ground, on hydrogen. Okay, so.
Thank you for this really insighting and interesting talk. Could I have 1 or 2 questions?
5.
We go for order. She was the first.
Okay, sorry. Thank you for the wonderful talk. I really have a very short question. When you said the predicted data, you mean the data from calculation, right?
Yeah.
Have you considered changing chemistry?
Yes.
Because the NOx can be related to that, no?
Yeah. We looked at, I skipped a lot of things, but yeah, we look at different reaction mechanisms, and I also, in the end, I'm using the same mechanism for kerosene as for hydrogen. It's a mechanism which is all developed by Warnards, but he started from hydrogen and extended it. But we also looked at San Diego, which gives similar results. GRI gives completely different results, so don't use that for hydrogen.
Just maybe you said that and I missed it. Did you do the annular combustion at high pressure or at atmospheric pressure at the test?
No, that's at high pressure.
High pressure.
We didn't go to the full pressure yet. We went to 13 bar.
Okay.
But the test we will do this month, we will go to the 30 bar.
Okay.
So.
I had a similar question on NANO, but it was partially addressed. We can talk about that later. You also mentioned the micro mix
Yes.
injector, and you say up to 60% reduction in NOx. I missed what is the the drawback? Is it just the manufacturing is more complex, so you expect more issues with that injection?
Yeah, the manufacturing is more complex, and then you also have a lot of thermal problems because the hydrogen is cold and the air is hot, and then already in some of our injectors. In the end, our choice of the injector in the end was made because of the one with the less thermal stresses.
Thank you for the presentation. Yeah, it's interesting that NOx isn't significantly increased, so that's a good takeaway. Have you looked at, or do you have plans for looking at the other main pollutant, water, specifically in the form of contrails? Is that something that can even be done computationally, for example?
Yes, but also can do it on a piece of paper. You know the air fuel ratio
no,
in
I
a
know
computer.
how much water comes out, but whether or not it forms a contrail is different.
Yeah, but from the combustion chamber, there's no contrail. It's only from the combustor. I know what you mean. Yeah. So from combustor concept, it's easy because you only have water vapor, which is hot, and then even from the engine, it's hot. But we also now are. There are some research projects where we work together with people which look at what happens in the atmosphere and contrails, because in the end, it's a big thing. Yeah. Because in the end, it's not clear what's better in the end, whether you have hydrogen or kerosene. And also the interaction, for kerosene, you have contrails because you have particles from the soot, which then form contrails, and hydrogen, you don't have it. So in the end, it's unclear what impact it will have.
Thank you.
One thing I noticed, though, is you have kilogram per second, but if you normalize by input of fuel, you'll have higher per kilogram of hydrogen. Of course, you have higher, isn't it? Because you need more air for kerosene, no?
No, the air is the same. So,
but the amount of fuel that you're putting in is almost half in terms of weight.
Yeah, one third. Yeah.
So
there are two things. I didn't go into that, but the emissions are normally in aerospace are defined in EEE, like a gram NOx per kilogram fuel. But at the end, if you look at the regulations, the CAPES, that's then again in thrust. So then it doesn't matter anymore. So.
All right, please join me in thanking Ruud again. Thank you very much.
Okay, thank you.